Welcome to the deep dive. Today, we're looking at something. Well, it's more than just the next step in cancer therapy. We're diving into a really clever molecular design that solves a problem immunotherapy has been wrestling with for a decade.
It really has.
We're going to unpack the engineering behind something called MITES, that's myeloid-targeted immunocytokines. Think of it as a molecular Trojan horse strategy aimed right at cancer's command center.
And that command center is exactly why this is so needed. I mean, we've seen incredible progress with checkpoint inhibitors, things like anti-PD-1. But the biggest hurdle, the reason patients relapse, is often the tumor microenvironment, or TME.
Right, the PME.
It's not just passive tissue around the tumor. It's an active immunosuppressive fortress that the cancer builds to protect itself.
Okay, so if the TME is the fortress, who's the general calling the shots inside?
That would be the tumor-associated macrophage, or TAM. These are immune cells that are basically co-opted by the tumor. They're corrupted, they drive tumor growth, they help it spread, and critically, they pump the brakes on any immune attack.
How do they do that?
One of the main ways is by expressing these inhibitory checkpoints, and a really key one on these cells is called TREM2.
Now, I know that just targeting these TAMs by themselves, as a monotherapy, it hasn't really worked out all that well. So why the obsession with them?
It's all about proximity. It's location. When researchers did spatial analysis on human tumors, we're talking lung, breast, ovarian, they found something critical.
Okay.
The TAMs and the killer T cells, they aren't in different zip codes. They are right next to each other. They're physically touching, interacting constantly inside that TME.
So it's not just about the bad cells, it's about the bad conversations happening between the cells.
That is the perfect way to put it. The TAMs are whispering these go-to-sleep signals to the T cells, causing them to get exhausted, so the mission became clear. You can't just attack one side. You need a dual targeting strategy.
So you have to shut down the suppressive TAMs.
Exactly. And at the very same time, you have to activate the good guys, the T cells, and the natural killer, or NK cells. You have to hit both the command center and refuel your own troops simultaneously.
Right, so that makes perfect sense. And the most straightforward way to do that, I guess, is to just bolt the two weapons together into one molecule, which is what they tried first, right, with this alpha-TREM2 IL-2SK ICK.
Exactly. An immunocytokine, or ICK, they took an antibody that blocks that TREM2 checkpoint on the TAMs, and they fused it directly to something called IL-2SK.
Okay, let's pause there because IL-2 interleukin-2, that's kind of the classic T-cell fuel, but it's famous for being, well, a bit of a mess. It causes nasty side effects.
It's a blunt instrument, yeah. And it activates both the killer T cells you want and the regulatory T cells, or TREGs, that you don't want.
So what's the SK part?
SK is for superkine. It's not natural IL-2. It's a synthetic engineered version. The clever part is that it's designed to bind much more strongly to one part of the receptor, the IL-2R beta subunit. And that little tweak is meant to preferentially rev up the killer effector T cells over the suppressive TREGs.
So even in this first draft, they were already trying to build in some precision and some safety features too, right?
They were. They put in what's called an Fc null mutation. It's a small change to the antibody's backbone, but it's meant to stop it from accidentally triggering other immune cells to attack things they shouldn't. So they were definitely thinking about safety from the get-go.
So you have this dual-action smart bomb. It targets the bad guys. It fuels the good guys. It seems like it should work.
Yeah.
What happened when they actually gave it to mice?
It was a catastrophe. A complete disaster.
Right.
They had created a systemic poison, just 2 small doses, and, well, in one of the trial groups, all 7 mice died rapidly.
Wow. So all that effort on the safety features, the Fc null, it didn't matter. Did they just unleash too much power?
They absolutely did. The problem wasn't the targeting antibody part, it was the cytokine, the IL-2SK. When you release that systemically, you get a massive off-target cytokine storm. They saw huge spikes in inflammatory markers like IFN-gamma and IL-6.
And it caused organ damage.
Oh, yeah. In healthy mice, it caused severe hepatotoxicity liver damage. You could see it in their skyrocketing liver enzymes, ALT and AST. The drug was working everywhere at once, and that was poisoning the whole system.
Okay. So that is the aha moment, the turning point. The problem isn't the weapon itself. The weapon is clearly powerful. The problem is delivery. You've built a bomb that just detonates everywhere instead of only inside the enemy bunker.
Precisely. The challenge completely shifted. It became How do we make this thing conditionally active? And that's what led to the myeloid-targeted immunocytokine. It's a prodrug. The whole idea is that the cytokine only switches on when it's right on top of its target.
Finding that perfect switch, though, that seems like the hardest part. You need something that's only in the tumor and nowhere else. How'd they even find that?
They did a massive data dive. They used single-cell RNA sequencing from all sorts of human cancers and screened for proteases. Those are enzymes that cut other proteins that were, super enriched in TAMs.
And one just popped out of the data.
One was the clear winner, MMP14, matrix metalloprotease 14.
And why MMP14? Why a protease?
Because a protease gives you surgical precision. MMP14 is not only highly expressed on TAMs, its expression was strongly correlated with TREM2, the very thing the antibody part was targeting. It's like a two-factor authentication system.
Yeah, that's smart.
Yeah, the antibody says, okay, I'm at the right address, and the protease says, yep, you're at the right door. Only then does the weapon arm itself.
Okay, let's really visualize this because this is the breakthrough. How did they build this molecular safety catch?
So you still have the anti-TREM2 antibody fused to the IL-2SK, but, and this is the key, the IL-2SK is completely disabled by a physical mask. They attached a piece of its own receptor, the IL-2R beta protein, right on top of it.
So it's like putting a cap over the end of a key so it can't go into any locks?
Exactly. It's a molecular condom. It physically blocks the active site. So as this molecule circulates through the body, the IL-2SK is totally inert. It can't activate anything.
And how do you get the cap off?
The cap is attached with a very specific little chain of amino acids. And that chain is the MP14 cleavage site. It's the fuse. So the mite travels through the body, totally safe. It gets to the tumor. The antibody binds to a TREM2 positive TAM. Then the MMP14 that's all over that TAM acts like a pair of molecular scissors.
It snips the fuse.
It snips the fuse, the mask falls off, and suddenly you have a fully active, incredibly potent IL-2 superkine that is released right there in that exact spot to activate all the nearby T cells and NK cells.
That is brilliant. Okay, so in theory, that solves the toxicity. Did it actually work? Was myeloid-144 their lead candidate? Was it safe?
It was a complete home run on the safety front. In mice, myeloid-144 caused no detectable systemic toxicity. Body weights were stable, no cytokine spikes in the blood, no liver damage, nothing. They had completely eliminated the risk of a cytokine storm.
And it was still getting to the tumor.
Better than before, actually. It had preferential tumor accumulation and a nice, long half-life of almost 12 hours, so it had plenty of time to find its target.
Okay, so they solved the safety issue. That's huge. Now for the big question, was it still powerful? Did it work against tumors?
The results were, frankly, pretty stunning. In the MC38 mouse model, myeloid-144 on its own almost completely stopped tumor growth. It blew away the monotherapies, just anti-TREM2 or just anti-PD-1. It wasn't even close.
Wow. That already proved the dual action concept works. But what about in combination? What happens if you layer this on top of existing immunotherapies?
That's where it got even better. They tried what they called the killer combo. They combined myeloid-144 with anti-CTLA-4 blockade. And that combo led to complete tumor eradication. In 6 out of 7 mice, the tumors just vanished.
Eradication, that's the word you want to hear. So to understand that incredible synergy, we have to look at what's happening inside the tumor, the single-cell data. What was this thing actually doing?
It was doing a total remodel of the TME, hitting both sides of the aisle. First, the myeloid reprogramming. It was forcing the TAMs to switch sides. It downregulated the suppressive genes, like TREM2 itself, and pushed the TAMs into a pro-inflammatory state. They started making stuff that helps kill tumors.
So it's flipping the enemy's command center, and at the same time what's happening to the troops, the T cells and NK cells, with all that fresh fuel.
That's the lymphoid activation. The NK cells went into hyperdrive. You saw this massive upregulation of killer genes like perforin-1, which is what they use to literally punch holes in cancer cells.
Okay, and the CD8 plus T cells, the main soldiers.
It did something more subtle and honestly more important than just making them angry. Yes, it made them proliferate, but it also promoted what's called stemness.
Temness.
Yeah, it upregulated a gene called TCF7. It means the T cells retain the ability to self-renew and persist long-term. And crucially, it downregulated the genes associated with exhaustion, like tox. So you get T cells that are not only activated, but are also durable and resistant to burnout.
That's a huge deal. And let's connect that back to the killer combo. Why was adding anti-CTLA-4 the secret sauce?
Well, the localized IL-2SK, for all its precision, did cause a slight increase in those suppressive Treg cells. It's just a known effect of IL-2. But adding anti-CTLA-4 completely abrogated or wiped out that increase.
Ah, So it cleaned up the one tiny side effect.
Exactly. It neutralizes the suppressive tregs while also taking the brakes off the effector T cells. So you're disrupting the TAMs, fueling durable T cells, and removing the last line of defense. And that's how you get from tumor control to total eradication.
So elegant. Okay, final piece of the puzzle. Does this work in humans? Or is it just a cool mouse drug?
Well, they tested that using patient-derived tumor fragments, or PDTFs. They took fresh tumor biopsies from patients with renal cell carcinoma and treated them in a dish.
Did the mechanism hold up?
It was a perfect match. In the
Yeah.
human tissue, MyTE-144 did the exact same thing. It selectively expanded the cytotoxic cells, the CD8 plus T cells, and the NK cells, while reducing the suppressive cells like TREGs and TAMs. The molecular signature was conserved.
That's the proof of translation you need to see. This really feels like a design blueprint that overcomes the issues that plagued, every other attempt at using cytokines this way.
It's extremely promising. Now, we do have to mention the limitations that the sources point out. This is still mainly mouse data and ex vivo human tissue. We still need long-term safety studies in, say, non-human primates and to see how it combines with chemo or radiation.
Of course,
Yeah.
of course. But okay, let's unpack this one last time. This MITE technology is a blueprint for a new generation of smart immunotherapies. It's a precision Trojan horse that solves both halves of the problem. It reprograms the suppressive environment, and it unleashes fully fueled, exhaustion-resistant killer cells, all thanks to a protease-activated safety switch. It's just incredibly elegant.
And that protease switch is so clever, it really makes you wonder, and this is a question for you to think about, if they can successfully use a tumor-specific enzyme like MMT14 to turn on this therapy, what other enzymes that are unique to the TME could we use? I mean, think about enzymes involved in metabolism or hypoxia. Could we design entirely different drugs that are activated by a tumor's specific metabolic fingerprint, tailoring the activation mechanism itself to each tumor type?
A compelling thought, building even more layers of specificity into the delivery. Thank you so much for breaking down all this complex data for us today. For those of you who want to go deeper, the original sources are available for you to explore.
My pleasure.
That's all the time we have for this deep dive. We'll see you next time.